Hello, in this video we present the design of a 4-bit binary counter which can be used as a general purpose or multiple purpose counter. It consists of the following. We need 4 flip-flops when the counter is 4 bits, so we call them A0, A1, A2 and A3, and in this counter we use a JK flip-flop. As we mentioned, this is a synchronous counter, so we have a clock that is connected to all the clock inputs of the flip-flops, and this counter also has a clear input which is connected to the clear inputs of all the flip-flops, so we can clear all of them at the same time. Now, J and K of the flip-flops will be connected with the count and the load through combinational circuit as we will describe now. Let us assume that count is 1 initially. So when count is 1 and load is 0, this will be here 1 and this will be 1 here. It will be 1 here and it will be 0 here. So if this is 0, look, we have zeros at all the inputs of these AND gates, and therefore the outputs of the AND gates will be zeros. This is 0 and this is 0. This is 0, 0, 0, 0, 0, and 0. And we find that each OR gate at the right-hand side has one input 0, whereas the other input comes from the count signal, that is 1 here. So this will be 1 here, 1 will be 1, and this is 1, 1, 1. And for the first flip-flop, J and K will always be 1s, and therefore A0 will complement at every clock pulse. Now, for A1, J and K of A1 will be the count, which is 1, ANDed with A0. This is A0, and this is A0 here. Therefore, this will be A0 and A0. So this will complement every time A0 is 1. Similarly, as we explained earlier, the J and K of the next flip-flop will be A0 times A1 times the count pulse, which means A2 will complement whenever both A0 and A1 is equal to 1. And finally, the input J and K to the third flip-flop will be A0, A1, A2. So this will be A0, A1, A2, and A3 complements whenever all three outputs are 1s, and so forth. And therefore, the counter will be counting up as usual. Now, this counter can be used for multiple functions. First, as a counter that we have just described, and the second, which is very important, is similar to a register which has parallel load capability as well. The parallel load will be implemented, will be done when the load is 1. And when the load is 1, look what will happen. This will be 0, and this will be 0, and it does not matter what is the value of the count, this here will be 0. In this case, we say that if the load is 1, we don't care about the count. And we say it differently. We say that count is inhibited when the load is enabled. So if precedence is to the load, not to the count. So when the load is active or enabled, the counter will load the inputs in parallel and it will not count. So let us examine this case then. When the load is 1, again, this will be here 0, and this will be 1, and this will be 1 here. This will be 1, and 1, and 1, and 1, 1, and 1. And therefore, the inputs I0, I1, I2, and I3 will appear either true or complemented forms at the outputs of the AND gates that are at the left-hand side. So this AND gate will have output as I0, and this AND gate will have I0 prime. Similarly, this will be I1, and I1 prime, and I2, I2 prime, and I3, and I3 prime. Now, looking at this gate, the output is 0 here. Therefore, this will be 0, all this line here. And this means that the OR gates will have, each OR gate will have one input as 0. This will be 0, and this will be 0. And the other inputs of the OR gates will come from I0 or I0 prime. So this will be I0, therefore it will appear here, and this will be I0 prime. Similarly, this will be I1, I1 prime, I2, I2 prime, and I3, I3 prime. And let us take one flip-flop separately and look at it. If the flip-flop JK is like this one here, and this is I, and this is I prime, and this is AI. Look, if I is 0, this will be 0, and this will be 1. This is the J, and this the K. It means K is 1, and J is 0, and therefore at the clock pulse, the flip-flop will clear, so this will be 0. On the other hand, if I is 1, this will be 1, and this will be 0. Therefore, as if J is 1 and K is 0, therefore at the clock, the flip-flop will set, which means this will be 1. So in other words, when we connect I and I prime to J and K, as we see in this diagram, I will be transferred to the flip-flop output simply. Therefore, when load is 1, the values of I0, I1, I2, I3 will appear at the outputs of the flip-flops here. So this will be I0, I1, I2, and I3. Finally, when all the outputs of the flip-flops are ones, when this is 1 and 1 and 1 and 1, and the count is enabled, we find that this will be equal to 1, which usually we take it to the next stage. Interesting counter, as a matter of fact, because it can be used for multiple purposes. Therefore, we represent this in a block diagram. So inside the diagram here, we see all the hardware that we have just described. And the counter will have the following. It will have clock input, a clear input, and count input, and load input to control the operation of the counter. And it will have 4 bits data in and 4 bits data out. And we have the C out that we have just described. Now, this counter is also represented by a function table, so we know how to use it. And the function table says the following. When the clear is 0, and if you remember, it is asynchronous clear, so it is independent of the clock. So we don't care what is the value of the clock. We don't care the value of load and count. The counter will clear to 0. So all flip-flops will become 0 asynchronously, irrespective of the clock pulse. For the counter to function, a clear must always be maintained at 1. So when the clear is 1 now, and the load is 1, as we have just described, we don't care about the count because the load inhibits the count. And the counter will load the inputs, which are I0, I1, I2, I3 to the outputs at the rising edge of the clock. In order for the counter to count, load must be 0, and the count must be 1. And when this is the case, and of course clear is 1, the counter will count to the next binary state when the clock goes from 0 to 1 at the rising edge. And finally, if load is 0 and count is 0, the counter will have no change. It will neither count nor load at the clock pulse. It will keep its state as it is. We mentioned that this counter purposes, general purpose, so we can use it actually in more than many different ways. We'll take 2 examples here of constructing a binary coded decimal counter using this counter here. The 2 cases, it is connected as follows. The first one, we connect all the inputs to zeros. and we connect the other inputs as follows. Of course, we have to have a clock signal coming, so it counts on the clock signal. The clear must be 1 in order to be able to count, and the count must be 1 so that it can count. And then, no matter what is the value of the outputs at the beginning, assume any value actually, when this reaches 1 and this reaches 1, this will be 1 here, and the load will be 1, and it will load the values of zeros. So when the counter is 0, so we can put here 0, 0, 0, 0. And when this is 0, 0, 0, 0, load will be 0, load will be 0, count is 1, therefore it will count at every clock pulse. So at the clock pulses, it will be counting from 0 to 1, 2, 3, 4, 5, 6, 7, 8, until it reaches 9. When it reaches 9, this will be 1 here, and this is 0, this 0 is 1. Again, this will be 1 here. And when this is 1, what will happen? At the next clock pulse, it will load the input 0. Therefore, it will continue to keep counting in binary coded decimal from 0, 0, 0, 0 to 1, 0, 0, 1. Now, there is one very important point here to remember or to understand. When the counter reaches the value of 9, it will not go to 0 immediately. It will go at the rising edge of the clock. Therefore, it will stay in state 9, 1 complete clock pulse, and therefore it counts from 0 to 9. So that's one way of using this counter to design BCD counter. Another way is as follows. We don't care what are the inputs. The inputs will have no effect here, but the load must be 0, so it does not load. And the count will be 1, so it counts. And there has to be a clock input, of course, in order to count at the clock. And then we let the counter count when the counter reaches 1, and this is 1, so it doesn't matter where do we start actually. When A3 and A1 is 1, this is a NAND gate. This here will be 0, and this will be 0. When a clear is 0, it will clear immediately, asynchronously, irrespective of the clock pulse. So when this is 0, the counter will go to 0, 0, 0, and 0. Now, as soon as it becomes 0, 0, 0, 0, this will be 1 again, and this will be 1 again, and the counter will start counting at the clock pulses. So it will go from 0 to 1, 2, 3, 4, 5, 6, 8, 9. After it reaches 9, at the next clock pulse, it will go to 10. 10 means 1, 0, 1, 0. As soon as it reaches 10, actually, immediately this will be 1 and this will be 0, because this is 1 here and this is 1. NAND gate 1 and 1 inverted 0. This will be 0 and it will clear. Therefore, it will go back immediately to 0. So the very important point here to notice is the counter stayed 1 complete clock pulse in each count from 0 to 9. However, when it reaches 1, 0, 1, 0, the counter immediately goes to 0, 0, 0, 0, which means the counter does not stay in the state 10 at all. It goes immediately to 0 because the clear is asynchronous. Therefore, this counter will count from 0 to 9 repetitively, as expected.